Okay, well then I will talk to you about the chain rule. The standard chain rule you learned in Calculus 1 and the consequences and implications of the chain rule for integration. And I will start with reminding you that model that I mentioned last time about the tank of oil. So you think about theoretically three-dimensional tank, but for me it will be a flat tank, and the tank is presumably filled with oil up to some level. And then we are going to be interested in the volume of the oil in the tank, and what we can measure is the level of the oil, and the volume of the oil in my case is going to be the area. It's really about the area, and the area depends on this level, right? So area becomes a function of that level x, and then there is no formula yet, but if we introduce coordinate system so that x-axis goes vertically and y-axis horizontally, then what we can recognize is that this side of the tank can be represented as a function y, a function of x, and then what we see here, the area, is exactly the area below that graph. So this way we can get a formula for the area. As a function of x, it's an integral from 0 all the way to x of that f of x dx. Now, a question I might want to ask is the following. What if the level changes? And I'm asking now, what if x becomes a function of t? Well then, I would like to know at this point the rate of change of the area with respect to time. So I need derivative of the area with respect to time. Because ultimately, if x is a function of t, then area becomes a function of t. Right? So it makes sense to ask for that rate of change, and that's where chain rule comes in. If you understand that our function a is a function of x and x is a function of t, and you want to differentiate with respect to t, the chain rule says a prime with respect to t is equal to a prime with respect to x times x prime with respect to t. Right? That's the standard chain rule. And what that means is that we can now differentiate the function a as a function of x. And that is exactly the fundamental theorem of calculus. So derivative of this integral with respect to x, where x is the upper limit, is simply the integrand evaluated at x. And of course, the notations will be possibly less confusing if I replace that inessential variable with something inessential. And again, t is useful for other reasons, but I can replace it with anything, something like theta. So this variable in the integral plays very artificial technical role. The essential entrance of this variable is only at one point. So I substitute this x into f, that's my derivative of the area with respect to x. Then I have to differentiate x with respect to time, and if that function is given or measured, then I get the answer as a product.